Hello all of you. So in the last lecture we discussed the mesoscale simulation methods, which are the methods aimed at working with longer length and time scales than typically possible in standard molecular dynamics or Monte Carlo simulations, particularly for atomic systems. And today I will discuss some of the case studies of the mesoscale methods that is taken from my own research. Of course, you can find many more elaborate studies on these methods, but I picked the ones that I have worked with. So, the first study I will discuss is for systematic coarse graining of the methyl cellulose molecule. And the reason why we wanted to do a systematic coarse grained simulation in this case is because we of course did atomistic simulations, but they were limited to very small molecular weights. The polymers that we wanted to simulate were having much larger molecular weights than compared to the ones we were simulating. And the second thing is that we wanted to simulate the aggregation behavior of these molecules because the methyl cellulose tends to form gels at higher temperature. We were interested in trying to capture that not only at a qualitative level but also at a quantitative level because we wanted to predict the behavior of methyl cellulose molecules. So, in particular, we were interested in what role the amount of the methyl groups on the polymer chain has on the aggregation behavior. And to look at the amount of the methyl group, there is a characteristics called the degree of substitution. So, every repeat unit of the methyl cellulose contains 3 positions where a methyl group can come in. So, what I am showing here is the backbone of cellulose. So, it is a cellulose molecule as drawn, and there are 3 sites where the hydrogen can be replaced by a methyl group. So, this is referred as 2, 3 and 6 sites. So, clearly the 6 is outside the ring and 2 and 3 are attached to the ring. Now, the degree of substitution is defined as the number of the methyl group per repeat unit, right. So, clearly for every repeat unit you can have 0 methyl group, 1 methyl group, 2 or 3. In the case of 3 you are occupying all the sites. In the case of 2 you can have 2,3 methyl cellulose that is occupying second and third site, or 3,6 or 2,6, or you can have a single occupation. In that case we will have a 2 methyl cellulose, 3 methyl cellulose, 6 methyl cellulose. In general, we are not interested in the substitution at a particular repeat unit, but an average value that is defined over all the repeat units, and that is how the classification of the methyl cellulose is typically done. So, the average substitution can vary from again from 0 to 3, and what we are interested in is knowing that whether substitution at any particular site, whether it is 2, 3 or 6, has a behavior different from that on the other site. That is the first part, and how much substitution has the characteristics of giving me the aggregation behavior or gelation behavior that we demand, or as opposite of that, what is the gelation behavior coming from, what is the corresponding degree of substitution or in the there. So, we can want to predict the relation between the degree of substitution of the polymer chain with their gelation behavior and aggregation behavior, and of course, we want to look at the behavior of polymer molecules themselves. So, the way we did that, and since the objective was to really simulate as long polymers as possible, we did somewhat aggressive coarse graining, and we said we will represent every repeat unit as one coarse grained entity. So, we have around 20 atoms in every repeat unit, and that becomes one coarse grained entity in our simulation. Of course, the coarse grained entities are mutually exclusive. There is no atoms in common, although I have drawn in here as them overlapping, but there are no atoms in common. So, these are basically my repeat units, which are represented using one coarse grained unit. So, we basically perform both atomistic simulations and coarse grained simulations. In the cases of low molecular weight, when we can do both, we use atomistic simulations to train the coarse grained model or parameterize the coarse grained model. And in cases where we cannot do atomistic simulations, we use the already trained coarse grained model to simulate the behavior for longer molecular weights. So, with this kind of a motivation, what we did was the atomistic simulations was performed in GROMACS. I will not go in details of the force fields and all that. They are in the paper that is referred to here. The coarse grained simulations are performed using Brownian dynamics in labs. We start with assuming a form of the coarse grained potential that includes a bonded interaction and non-bonded interaction. The bonded part is comprised of a bond interaction, an angle interaction and a dihedral interaction, and we assume some very simple form of these interactions. Kb and k theta are the strength of the bond and angle respectively. L naught and theta naught are the equilibrium bond distance and the equilibrium angle in the system. Similarly, we have a dihedral interaction where k phi is a measure of the strength and this term represents the phase of the dihedral. So, for the bonded interaction part, we perform the single chain simulations both in atomistic and coarse grained simulation, and basically we fit the coarse grained simulation to atomistic simulation by performing a variation of parameters in the coarse grained simulation. I want to emphasize here that since our model is very simplistic, we have actually used fewer number of CG units because every 20 atom that we have roughly in every repeat unit is considered as one CG unit. The simulations in CG model is pretty quick and therefore we can perform many of these simulations in relatively less time, and that is how we can basically fit atomistic results by performing many coarse grained simulations, but fewer atomistic simulations. So, this is one example of the property that we computed to compare against. So, we are here comparing the radial distribution function of the atomistic and coarse grained simulation. What you see is that the blue line is coming from the atomistic simulation and the red dots are coming from the coarse grained simulation, and you see that agreement is pretty good. It is capturing not only the height of the peak, but almost every peak that we have in the simulation. These peaks, which are rather small here, are also zoomed in, and you can see the agreement is pretty good over all the peaks that we care about. More importantly, I would like to emphasize here that it is not that we started with this model to begin with, because whenever you have any coarse grained problem, you do not have any starting point for the interaction model unless you are getting it from potential of mean force. So, one has to think the other way around and start with the model containing minimum possible number of parameters and try to see how much of the physics that we have gained, and if further details are needed, then only more terms are added. So, first for example, we had only bond parameters and then we saw how the radial distribution function is being matched. Then on the basis of that, we figured that maybe we also need an angle interaction. Once we have done the angle part, then we thought that something else is still lacking and we can add a dihedral part and so on. So, at every step of the coarse graining procedure or the model building in the coarse grained model, we have to, as a rule, always think that what is the minimum set of parameters that we have that will have the same representation of the behavior that we really want. Means we are not really concerned on building a coarse grained model that can exactly reproduce every possible result in atomistic simulation, because that would be, as I was telling in the last class, will be same as the atomistic model, that is every atom is a CG unit. So clearly the goal is not to have something that is more accurate, but the goal is to have something that is reasonably accurate yet efficient, and that was the, I would say, the objective behind our coarse grained simulation, because we wanted to really extend it to longer molecular weight chains. So something that would not only capture the behavior of atomistic simulations, but can also be applied to long chain simulations. So next we move to looking at the non-bonded interactions. So we modeled it using the Lennard-Jones 6-9 potential that contains the repulsive part going like 1 over r to the power 9. What we had discussed earlier had the repulsive part like 1 over r to the power 12. Of course, we had tried that, but we figured that maybe this will be better than that in terms of accuracy. The attractive part is the same as earlier. So as I have been telling you earlier, this has really a physical meaning. It comes from the theory of the van der Waals interaction, and this part is kind of arbitrary, but basically it characterizes the softness of the particles in the picture. The higher powers we go, it becomes more and more hard, but we figured that keeping it 9 gave us the fit that was desired. Again, there is no particular reason why we cannot think of any other potential that will fit. So there is no unique mapping when we think of a coarse grained model. It is only one of the possible coarse grained model that we could have built. And finally, the strength of the Lennard-Jones interaction was obtained using the iterative Boltzmann inversion scheme. That is, we took the atomistic simulation RDF as the target and we varied the parameters, in this case the Lennard-Jones parameter, to fit the atomistic simulation RDF. But in this case, we are looking at the radial distribution function of the multiple chain system as opposed to the single chain system, because for single chain system we have already used that to get the bonded parameters. So now we perform simulations of a multiple chains and look at intermolecular radial distribution function, and we fit that using the iterative Boltzmann inversion scheme and get the fitting parameter as the Lennard-Jones interaction strength. And this is what it looks like, and I am doing it for two different temperatures, again because I was interested in the aggregation behavior and gelation behavior, and in this case the behavior is different at different temperatures, and therefore we performed simulations at two different temperatures. And clearly what you see, this red and blue lines are basically data from atomistic simulations and coarse grained simulations. So these are for two different temperatures, that is 25 degrees Celsius and 50 degrees Celsius. We have done it for a variety of chemistries. So C refers to cellulose, 3-MC is 3-methyl cellulose with methyl being at 3 position, 2,6 is for 2,6 position and it is a homopolymer containing the same repeat units, and 2,3,6 where all the positions are occupied by the methyl group, and agreement across all the chemistries is quite reasonable between the atomistic and coarse grained model. So we can be confident that the aggregation behavior will be captured by the coarse grained model that we build. This also can be seen by looking at the snapshots of atomistic and coarse grained simulations for the systems for which we can do both atomistic and coarse grained simulation, that means smaller molecular weight polymers. And you see from the snapshots that the aggregation behavior is quite similar between different chemistries that we had simulated. Let us say when we go from cellulose to 3-methyl cellulose to 2,6 and 2,3,6, clearly as we increase the methyl groups, the aggregation should enhance because the polymer becomes more and more hydrophobic, and eventually it should form kind of formation of, I would say, tight aggregates or packed aggregates, and this is what is indeed seen both in atomistic simulations and coarse grained simulations. Finally, we looked at the radius of gyration of the individual chains, and this is where the strength of the systematic coarse graining starts showing up, because I am now probing to much longer chains than we can possibly simulate using atomistic simulation. Atomistic simulation is down here, this is all we can do, and under that regime, the polymer is what is known as a Kratky porod polymer, that is in the rod-like regime. It is something that we should not even call a polymer because it is not flexible enough. Only when the molecular weights are beyond certain number of monomers, around say 50 or 60 monomers in this case, the flexible nature starts showing up. And beyond that point, we cannot clearly do the atomistic simulations, but we can always do the coarse grained simulations. And the agreement generally was pretty good between the available experimental data and the simulations we conducted. Of course, there were a couple of outliers at higher temperatures, and we had attributed this to some sort of a ring formation that we see in our model, but that also has experimental significance. Again, I will not go in details here. The main point is that the systematic coarse graining is able to really push the length scales that we can simulate to a level where we can make quantitative predictions even for much realistic systems. And in this case of polymers, I think this is one of the only possible ways to go about, because clearly we cannot simulate very large molecule or very long molecular weights. The next case study that I will discuss is kinetic Monte Carlo simulations. As I have said, this is very similar to the Brownian dynamics simulations, except that we are doing in the Monte Carlo fashion and we associate every Monte Carlo step to certain time step. In this case, we are interested in looking at the self-assembly of photo-switchable nanoparticles. So, these are fancy nanoparticles which have certain ligands on them which respond to light. So, when you, for example, turn on the UV light, the ligands change configuration and they can become a cis state, or they can come back to trans state when the light is turned off. So, we can go from a trans state to cis state by turning on and off the UV light. Now, what is the interesting bit of it is when it is in the trans state, these ligands on the surface of the nanoparticle have zero dipole moment. Dipole moment of the molecule cancels out. So, between the two nanoparticles in the system, or any two nanoparticles in the system, we have no dipole-dipole attraction because the ligands have no dipole moment. On the other hand, when they are in the cis state, then they have a dipole moment, and therefore, we have an attraction between the nanoparticles because of the dipole-dipole attraction. So, what we can then have is a system containing nanoparticles whose interactions can be turned on and off or can be tuned by exposing them to light of different wavelengths. And this is precisely what they have done in this particular study, where they have varied the number of ligands in the nanoparticle, they have varied the solvent and so on. They looked at how the nanoparticles self-assemble in response to the light, and when do we have the cases where we have a clear reversible transition between an aggregate to a dissolved solution. So, with this kind of motivation, again the system was large enough for applicability of any atomistic simulation. Nanoparticles pretty much have size of the order of like 5 nanometers, that will have plenty of molecules, and we are not looking at one particular nanoparticle. Of course, they have plenty of ligands on top of them, they contain plenty of atoms, and the system itself contains, I would say, moles or very large number of the molecules in the system. So, clearly atomistic simulation is not the way to go, except if we are interested in things happening near the surface of the nanoparticle. If we want to look at the aggregation behavior, we have to go for the coarse grained model. And in this case, we were not interested in actually predicting the experimental data, but we wanted to make qualitative predictions, and therefore we used a generic coarse grained model. So, the kinetic Monte Carlo simulations were performed in a similar manner that we have discussed earlier. We had a fixed step size. but we didn't use the Metropolis criteria, we used a slightly different criteria. It is referred as the Glauber transition rate. And in fact, we showed that using this particular definition of transition rate, we can pretty much recover the diffusion equation, or this pretty much is same as solving diffusion equations, that is same as Brownian dynamics. So, it provides a clear mapping between the Brownian dynamics or diffusion equation by doing a Monte Carlo simulation. And the time step compared to every Monte Carlo sweep, that is when I try movement of all the particles in the system, is something that is given by this, where A is my step size and D is my diffusion coefficient. In here again, D is taken constant here. One may argue that D need not be constant, but in this case the idea was to get more a qualitative behavior than making any actual quantitative predictions, and in that respect the model was pretty good. So, we looked at a variety of things. First of all, we looked at the effect of temperature on the system, and we looked at what will happen when I go from UV state to a visible state. And the way we modeled that was using very simple Lennard-Jones interaction. So, we used a Lennard-Jones interaction with an attraction part when we were doing the UV light, and we used a Lennard-Jones interaction with no attraction part. The repulsive part is common in both, but attraction was not there when we are doing the visible light. So, UV will correspond to the case when we have cis ligand, and vis will correspond to the case when we will have the trans ligand, right. Now, clearly this is done in a manner that we can change the interaction between an ongoing simulation. So, we can pretty much run cycles of UV and visible light, and within a cycle we can have some interaction that is given for that cycle, and in the next cycle we can have some other interaction. So, we run it in cycles. In the cycle of UV light, we used the Lennard-Jones with attraction part, and in the cycle of visible light we used Lennard-Jones with only the repulsive part, and we performed many cycles to look at the effect of the periodic exposure of light to this particular system. And clearly we see that as the UV light is turned on, the nanoparticles begin to aggregate, and as the UV light is turned off, the nanoparticles begin to dissolve, and that is pretty much we see. So, this is the condition when the visible light is turned on for some time, because clearly aggregate will take some time to dissolve. So, if we give it enough time, it will become a solution. On the other hand, if I keep it in UV light for enough time, it will form an aggregate. We can also look at this as a function of the density of the nanoparticle in the system, and clearly we can have a transition between various possible states. So, this is the effect of density here. So, as we go to higher density, we can form larger and larger aggregate, and eventually for very large aggregate we can form some kind of a percolated structure in the system. So, in general the aggregate size will increase with the increase in density, and the gel structure will form at higher density in the system. We can also characterize the structure in a variety of ways. So, we can have the measures such as the average number density of the particles and the polydispersity of the entire system, and we can see how the aggregate size changes as a function of the parameter, right. So, for example, with increasing theta, the aggregate size increases, followed by a decrease at large theta value. Now, to look at that particular factor, we can look at what really happens with theta here. So, what is happening here is at very small value of theta, we have strong interaction between the particles, and in that case, once the two nanoparticles come together, they form an aggregate, but then these aggregates which are formed, they move rather slowly and find other aggregates. That means many of the moves in the Monte Carlo simulation get rejected as soon as one aggregate is formed, because they are bound too strongly with the other nanoparticle. As we increase the temperature, the interactions between the nanoparticles weakens. Now the aggregates still form, but the aggregate may merge with other aggregate more easily because the bond is not too strong. The particle can move out and form bond with some other aggregate, and I am talking about physical bond as opposed to any kind of a chemical bond. So therefore, although it is not quite intuitive, the largest aggregate size is actually found when we are at intermediate value of temperature, not at very low temperature. Although the strength of the interaction is very strong at low temperature, it doesn't give me a large aggregate size, because once they form these small aggregates, they do not further evolve because they diffuse rather slowly after formation of this, and that happens because of the strong interparticle interaction that prevent the movement of the nanoparticles. At very high temperature, as we may expect, we will have a solution because there is no interaction pretty much, or very small interaction. In this case, the entropy will dominate and the particle would like to be dissolved in the solution. This is precisely what we see here, and this is the behavior that we also get here, that the average aggregate size increases with temperature first, followed by a decrease at very large temperature, where the interaction strength becomes much smaller in comparison to the thermal energy of the system. We can also characterize the polydispersity, and it is shown in here, and as you may expect, polydispersity is highest at intermediate values of theta, and that happens because that is when we have multiple aggregates in the system, and once we have multiple aggregates, that will give rise to higher polydispersity. We can also look at the effect of density, and again you can see, since I was talking about formation of a percolated structure, this is where we see that the aggregate size actually increases significantly at very high density, and that is when we have the formation of percolated structure. At the same time, the polydispersity actually comes down, because once we have the percolated structure, then we have pretty much a single large aggregate spanning the entire simulation box, and that has a polydispersity of 1, because you do not have aggregates of different size in the system. So, polydispersity in this case represents the variation in the size of the aggregate. Once it forms like a percolated structure, you have only one aggregate in the system, and therefore polydispersity first increases but then decreases to 1. We also looked at other things, such as what will happen if I do not turn off the interaction immediately, but we turn off at a certain rate. That means the interactions will be slowly brought down to from UV to visible interaction, and that was the purpose of this was that the nanoparticles appear to have some memory, so they will take some time for losing their dipole moment, and this effect was also captured in our simulations. The key idea that I wanted you to take from this example is that we can study a variety of systems using the molecular simulations. Depending on the requirements, we should pick a model. If our objective is to understand the physics behind the process, then we can pick a generic coarse-grained model, and with rather inexpensive simulations, we can look at the physics behind it. On the other hand, if we really want to be quantitative, if we want to compare to experiments, then we have to go to either atomistic simulations wherever possible and systematic coarse-grained simulations wherever it is not possible. And then, as we had discussed, we have methods to tackle the free energy calculations and other methods to look at rare events and so on, that can be applied as appropriate. So, we should not think in terms of the method first and application next, but we should think in terms of the application first and then choose a method appropriate for the problem that would be computationally feasible with whatever goals that we have in mind. And in most cases, simpler models are much better than more complicated models, because simpler models can be, first of all, easily run and coded, and secondly, they are able to capture the qualitative behavior without the need for running over many parameters, because simpler models also have fewer number of parameters to work with. So it is always better to start with simpler models and then refine it, as opposed to starting with a complicated model and get lost with the number of parameters that you have in the system. But there is no hard and fast rule on that, but you always should have the application in your mind. So with that, I want to conclude today's lecture. Thank you.